Hello student, in this video we will be looking at question related to static equilibrium. A 20 kilogram floodlight in a park is supported at the end of a horizontal beam of negligible mass that is hinged to a pole as shown in the figure. A cable at an angle of 30 degrees with the beam helps to support the light. Find A. The tension in the cable, and B. The horizontal and vertical forces exerted on the beam by the pole. The first thing that we need to do is we have to draw the free body diagram of our beam. So this is going to be our beam. And then now we're going to be drawing all of the forces acting on the beam. First of all, we can draw the weight caused by the floodlight. So W, and then because this is the weight caused by the floodlight, it is going to be WF. And then we can write down it is going to be mass of the floodlight multiplied with G. The mass is 20 kilogram multiplied with 9.8. It is going to be equal to 196 Newton. Moving on, we have this cable at an angle of 30 degrees with the beam. So this is going to be the tension in the cable. And the angle, we can write it down here as 30 degrees. Moving on, we have additional two forces due to the connection between the beam and the pole. So the first one is going to be the reactive force or normal along the x component, because the beam is rested with this orientation to the pole. And another one we will have Ny or Ry, the reactive force along the y component. To solve the first question, finding the tension in the cable, we will be utilizing the first equation. In total, we have three equations. The first one, total force along the x component must be equal to 0. Number 2, total force along the y component is equal to 0. And then the last one is total torque is equal to 0. So these three conditions is important for any object to be in a static equilibrium. So we will start with the first one, total force along the x component is equal to 0. And if we inspect the diagram, we see that there will be two forces. Right away we can see an x, and then it is positive because it is to the right, plus with the tension along the y component. Right, so if you cannot see why we have tension on the x component, we can resolve tension to two components, which is Tx as well as Ty. And we can transform this into a triangle where this is going to be the hypotenuse, the true tension, and we have Tx as the horizontal base of our triangle, and then we have the vertical side of the triangle, which is Ty. And then we're going to put the angle 30 degrees here. So if you use cos 30 degrees, it is equal to the adjacent, which is Tx, over the hypotenuse. So moving back to our solution, total force along the x component is going to be Nx plus with negative direction of Tx equal to 0. So in the end, nx is equal to negative tx or negative t cos 30 degrees based from this derivation. As you can see here, we have two unknown. Remember that normal and tension doesn't have exact formula to calculate the value. And because of that, we're going to proceed to the second equation, which is total force along the y component is equal to 0. If you look at the free body diagram, in total, there will be 3 forces. First of all, Ny positive because it is upward, and then plus with Ty also positive because it is upward direction, and then plus with negative Wf. Reason being because Wf is directed downward direction. So in the end, Ny plus with T sine 30 degrees minus with Wf, which is 196 Newton, is equal to 0. Again, we cannot solve the question because we have two unknown, which is Ny and T. Moving on, now we're going to be using the third condition or the third formula for an object to be in static equilibrium, which is total torque must be equal to 0. Meaning that it is not going to be rotating because all of the torque is counteractive towards one another. Moving on, in this case, we have to decide on which point are we going to put the axis of rotation. A tip here, axis of rotation should be placed where we have the most unknown. And then in this case, we're going to put at the left end of the beam. And then rightfully because according to the question here, the horizontal beam is hinged to a pole. So this is our hinge or our axis of rotation. Okay, so because this is our axis of rotation or the hinge, now we have to take a look at the two forces at the other end, and then these two forces will be creating the torque, which is tendency of a force to rotate an object. And then if you take a look at the tension here, because it is directed upward, or if we refer to the hinge, it is directed counterclockwise direction. So this is going to be the direction of the torque. So in this case, it is going to be creating a positive torque. And then we have the weight, which is directed downward direction. And then the weight here will rotate the beam downward direction. So we can write down this is going to be the torque, negative torque, because it is clockwise. And then this is the torque produced by the weight of the floodlight. So now we can put in the two torque here. The first one, positive torque, if you recall, it is going to be due to the tension, and then plus with the negative torque, which is due to the weight of the floodlight. And it is going to be equal to 0. Positive and negative of torque is actually showing the direction either counterclockwise, positive torque, or negative torque, clockwise direction. So write down for reference, the equation for torque is going to be, I'm going to write it here, torque is equal to Rf sine theta, where R is the moment arm from the point of the axis of rotation to the point where the force is being applied. So this is the moment arm. and then substitute force with this function of sine theta. So for the first one, which is going to be the torque produced by the tension here, the total length is not given, so we're just going to put this unknown r and then multiply with the tension and then sine 30 degrees minus with, again we start with the moment arm, because the weight is at the other end of the beam, the full length of the beam is used, but because the length of the beam is not provided, so we're going to be using r again, and then the weight we're going to substitute with the calculated value 196, and then sine, in this case 90 degrees, because the weight is directed downward direction. So it will be creating an angle of 90 degrees with the moment arm. Sine 90 degrees is going to be equal to 1. So we can eliminate this, and then I'm going to rearrange the formula, so it will be reduced to just r multiplied with t sine 30 degrees. It is equal to, in this case, r multiplied with 196. Remember, sine 90 degrees is equal to 1, so we can just neglect by writing the value into the formula. So r appears now in both sides of the formula. We can eliminate r, and then in the end, to calculate tension, it will be 196 divided by sine 30 degrees. The tension is going to be equal to 392 Newton. So this is the correct final answer. To solve the rest of the question, which is finding the horizontal and vertical forces exerted on the beam by the pole, you can just substitute the value of tension here into the first equation for an x and the second equation for an y.